Has it ever struck your curious mind how 4G evolved from simple push-to-talk system? Is there any governing body which regulates the spectrum? What kind of services we will have in next generation of communication? So friends, let's start the journey of wireless communication. Mobile radio telephones were introduced for military communications in the early 20th century. Car-based telephones was first tested in St. Louis in 1946. This system used a single large transmitter on top of a high-rise building. A single channel was used for sending and receiving, similar to a half-duplex system. To talk, the user pushed a button that enabled transmission and disabled reception. Due to this, these became known as push-to-talk systems in the 1950s. To allow users to talk and listen at the same time, IMTS, Improved Mobile Telephone System, was introduced in the 1960s. It used two channels, one for sending and one for receiving, bringing telecommunication to full duplex mode.
In the 1970s, private companies have started developing their own system to evolve existing system further. Those private systems are Analog Mobile Phone System, used in America; Total Access Communication System and Nordic Mobile Telephone, used in parts of Europe; and Japanese Total Access Communication System, used in Japan and Hong Kong. Independently developed systems are called as first-generation communication. It was introduced in 1982 by Bell Labs and popularly known as Advanced Mobile Phone System, AMPS. The key idea here was to divide geographical areas into cells, and each cell was served by a base station so that frequency reuse can be implemented. As a result, AMPS could support 5 to 10 times more users than INTS. Major concern for the first generation was weak security on air interface, full analog mode of communication, and no roaming. Now, to implement roaming, individual organizations started working under one umbrella, European Telecommunications Standards Institute, ETSI, and developed second-generation system.
Second-generation cellular telecom networks were commercially launched in 1991 in Finland based on GSM standards. It could deliver data at the rate of up to 9.6 kbps. Three primary benefits of 2G networks over their predecessors were: phone conversations were digitally encrypted. It was significantly more efficient on the spectrum and allowing far greater mobile phone penetration level. 2G introduced data services for mobile, starting with SMS text message.
Further, to achieve higher data rates, GSM carriers started developing a service called General Packet Radio Service, GPRS. This system overlaid a packet switching network on the existing circuit-switched GSM network. GPRS could transmit data at up to 160 kbps. The phase after GPRS is called Enhanced Data Rates for GSM Evolution. It introduced 8 PSK modulation scheme and could deliver data rate up to 500 kbps using the same GPRS infrastructure.
During this time, the internet was becoming popular and data services were becoming more prevalent. Post 2.5G multimedia services and streaming started growing, and phones now started supporting web browsing. Development of 3G. 3GPP-UMTS, the Universal Mobile Telecommunications System, succeeded EDGE in 1999. This system uses wideband CDMA to carry the radio transmissions, and often the system is referred by the name WCDMA.
Now, before we go further, let us understand how the governing bodies were developed. In the interests of producing truly global standards, the collaboration for both GSM and UMTS was expanded further from ETSI to encompass regional standards development organizations such as Ariban TTC from Japan, TTA from Korea, ADAS from North America, and CCSA from China. The successful creation of such a large and complex system specification required a well-structured organization. This gave birth to 3GPP, which worked under the observation of ITUR.
ITUR is one of the sector of ITU. Its role is to manage the international radio frequency spectrum and to ensure the effective use of spectrum. ITUR defines technology families and associates specific parts of the spectrum with these families. ITUR also proposed requirement for radio technology. 3 organizations started developing standards to meet the requirements proposed by ITUR. 3GPP, 3GPP2, IEEE. Evolution of 3GPP started from GSM to long-term evolution advanced. Evolution of 3GPP2 started from IS-95 to CDMA revision B. Evolution of IEEE started from 802.16 fixed WiMAX to 802.16m. Since 3GPP was dominated and widely accepted, we have only incorporated roadmap evolved by 3GPP. Now coming back to third generation.
The goal of UMTS or 3G wireless systems was to provide a minimum data rate of 2 megabits per second for stationary or walking users, and 384 kilobits per second in a moving vehicle. 3GPP designated it as Release 99. The upgrades and additional facilities were introduced at successive releases of the 3GPP standard. Release 4. This release of the 3GPP standard provided for the efficient use of IP. This was a key enabler for 3G HSDPA. Release 5. This release included the core of HSDPA. It provided reduced delays for downlink packet and provided a data rate of 14 Mbps. Release 6. This included the core of HSUPA. With a reduction in uplink delay, it enhanced uplink data rate of 5.74 Mbps. This release also included MBMS for broadcasting services. Release 7. This release of the 3GPP standard included downlink MIMO operation as well as support for higher order modulation of up to 64 COM. Either MIMO or 64 COM could be used at a time. Evolved HSPA Plus provides data rates up to 28 megabits per second in the downlink, and 11 megabits per second in the uplink.
This brings us to the most awaited part, 4th generation system, long-term evolution. Initial goal of telecommunication was mobility and global connectivity, but as the technology evolved, the services started expanding. Now services were not restricted to voice and SMS only. For this expansion and efficient execution in long-term evolution, whole new architecture was adopted for both non-radio part, which is SAE, System Architecture Evolution, and radio part, using pure IP architecture, packet switching. To fulfill the requirement proposed by ITUR, study group formed, and LTE standardization began in 2004. Large number of telecom companies collaborated to achieve their common vision. In June 2005, Release 8 was finally crystallized after series of refining. Some of the significant features of Release 8 were reduced delays for both connection establishment and transmission latency, increased user data throughput, increased cell edge bitrate, reduced cost per bit, implying improved spectral efficiency, simplified network architecture, seamless mobility, including between different radio access technologies, reasonable power consumption for the mobile devices. These requirements were fulfilled by advancement in the underlying mobile radio technology. The 3 fundamental technologies that have shaped the 4th generation system in the radio interface were multi-carrier technology, multiple antenna technology, and the application of packet switching to the radio interface. As a result of intense activity by a larger number of organizations, the specifications for the Release 8 was completed by December 2007. The first commercial deployment took place by the end of 2009 in Northern Europe. In the subsequent releases, multiple services such as multi-cell HSDPA, HETNet, coordinate multipoint, carrier aggregation, massive MIMO and many more were targeted for a rich customer experience.
Now it's time to move from services to multi-services approach. In other words, from LTE Advanced to Next Generation Communication System, which is 5th generation. Features have been planned to be added in the 5th generation or Next Generation system are pervasive networks, where a user can concurrently be connected to several wireless access technologies and seamlessly move between them. Group cooperative relay. This is a technique that is being considered to make the high data rates available over a wider area of the cell. Cognitive radio technology. It would enable the user equipment to look at the radio landscape in which it is located and choose the optimum radio access network. modulation scheme and other parameters to configure itself to gain the best connection and optimum performance. Smart antennas. Another major element of any 5G cellular system will be that of smart antennas. Using these, it will be possible to alter the beam direction to enable more direct communications and limit interference, also increase overall cell capacity.